All right, it's definitely time to start. So everybody go ahead and chat me your first and last name if you haven't done so already, so I can have you for my roll. Feel free to turn on transcript recording or closed captions or any of that kind of stuff if you want to. We are in chapter 8. I've done essentially everything we needed for chapter 7, and I had even to some extent hinted at what's going on with chapter 8. Chapter 8 is about conservation of energy, and specifically, I talked about, wrong side. I talked specifically about conservation of energy uh, in terms of some mathematical theorem where basically we said, condition one, F is a conservative force, and then condition two, the that triangle operator, which is called del or gradient or nabla, when you take the cross product of that with a force and you get an answer that's identically zero, meaning you don't have to plug in a specific value of x, y, and z to make it zero, it just automatically comes out zero. When that's the case, then it's definitely conservative. And the way this theorem works is I've given you like five or six different facts, and once you prove one of them is true, it's automatically so that all of them are true. So a lot of people don't even separate what I called number one, which is F is a conservative force, and number two, which is the it's technically called the curl of F when you do the del cross F. So when the curl is zero, that's the same thing as meaning the force is conservative. So sometimes you just have, instead of step one, the force is conservative. Step two, the curl of the force is identically zero. Sometimes that's just step one. Then it said that if you take the integral from A to B, in other words, calculating the work done from any point A to any point B, is the integral of f dot dl, and that turns out to be equal to u of b minus u of a, and is independent of path. So that's the normally what I call the third condition. And it's very important that not only is it independent of path, but it's specifically some u of b minus u of a, meaning it only depends on the endpoints, not the actual path you took. Another version or another line, the fourth statement was that the work done in any closed loop. So if you imagine any path you want, you can do anything you want as long as you start and stop at the same position, then that's called a closed integral of the work. So you're actually calculating the work done in a closed interval over a closed path, if you will. That's always equal to zero. And then there's another step, number six, say, that says there exists a scalar potential U such that F is equal to the negative gradient of U. So that's really the big mathematical principle behind this. There's another one in there as well that deals with some differential equation stuff. I don't really remember the wording of that so well, so I don't usually tell you that. And plus, it's way beyond this course because you're normally not going to have differential equations until at best the second or third semester of your calculus course, if you have it even before your calculus is over. Most people don't have it until after it's over, so it's a little unnecessary for me to cover that. But anyways, that was a lot of the stuff that came from chapter 8, even though we did it in chapter 7 and talked about it then. So I just want to remind you, chapter 8 does go over that stuff to some extent, and they remind you, like I did, that once you have a force that you think is conservative, you can calculate the potential energy of it by taking the integral of f dot dl to calculate work. But in this case, you calculate the work from, some arbitrary point in space to some arbitrary point in space. So from some arbitrary point A to some arbitrary point B. If you calculate the work done in going from A to B, excuse me, uh, using the force that is what we call the conservative force, then the negative of that work done is equal to the change in potential energy. So setting that equal to some U final minus U initial gives you the ability to figure out exactly what the function u final is, and therefore also what the function u initial is. So that's a whole different way. That's a way that you've now learned about how to find the potential energy for a given conservative force. We did that with the force being F equals negative mg j hat. And from that, we discovered that the potential energy was mgy. And if you go and take the force being negative mg j hat, you should be able to get the force out of that potential energy, which is U equals mgy. And all you have to do it is take the negative of the derivative of U with respect to y. And lo and behold, if you take the negative of the derivative of mgy with respect to y, then you end up getting just plain negative mg. And then, of course, you have to multiply it by j hat. So that gives you the force not only in magnitude, but in direction. So that's another thing that we covered. Now, what I'd like to do is show you how we're going to use that. And specifically, I'm going to show you the book's ways as well as the way that I tend to teach my students conservation of energy. So we'll start off with the typical scenario, conservation of mechanical energy. I'm going to share my screen with you in a second. Let me get this other person in. Conservation of mechanical energy. Whoa. Now, this is mechanical energy right now, but we are going to eventually get to the point where we are taking into account internal energy and nuclear energy, meaning the energy of the nucleus, not necessarily nuclear power, but that is one and the same too, and that sort of stuff. But that will not come till like chapter 17, 18, 19, and 20. So I'm going to go ahead and share my screen with you guys. Here it is. It should come up in a second. So, to deal with conservation of mechanical energy, I got to tell you what the mechanical energy is. So, the types of mechanical energy are potential energy and kinetic energy. So, potential energy is one of them, kinetic energy is another one. And depending on how you splice it up, or slice it up, I should say, you can, in principle, get a couple different types of potential energy. So you can, for instance, have U is equal to mgy, and you're allowed to say y equals 0 at any height you want. Doesn't matter at all. Okay, that's not going to matter at all. We'll show you an example of that in a little bit. So that's one potential energy. But sometimes people use potential energy to represent the energy stored in a spring, and that was from the force F equals negative kx, or Hooke's law. And from that one, we learned that the potential energy was 1 half k x squared. We also have, for instance, if we're dealing with distances away from the surface of the Earth that are comparable in size to the radius of the Earth, then the MGY doesn't work anymore. So in that case, I'm going to put quotation marks around this because I'm just spilling it out off the top of my head. There's a chance that I might be forgetting a term or something like this, but I'm pretty confident it's U is equal to negative G M lowercase m over plane R, and that's the one I put in quotation marks. So those are some of the different types of potential energy we could use. That U equals negative GMM over R is the potential energy that you'd have at a distance R away if your mass is M and you're a distance R away from your mass big M. Okay, and the mass big M is supposed to be like the mass of a planet or a moon or an asteroid or something like that, and the little m would be your mass. So that's some of the different potential energies. We also have kinetic energy, which right now we only know of as kinetic energy equals 1 half m v squared, but it's later going to turn out that there's also a kinetic energy due to rotation, and that's 1 half I omega squared. So that's some of the terms we could deal with. So conservation of energy is often represented as delta U plus delta K. Actually, I should use a uppercase K there. Plus delta K is equal to zero. So that's one version of conservation of energy, and that's the one that your book tends to use most often. Now, if you remember that delta blank is defined to be blank final minus blank initial, meaning whatever symbol you put in this little blank right here is going to be in this blank and this blank as well. So this could be a U or a K or a V, and then this has to be the same U or K or V, whichever one you used. So that's what that means. Now that we've expressed that as the case, then you can see that this is equivalent to U final minus U initial plus K final minus K initial is equal to zero. And you can rearrange that to get U, whoa, Nilly. You can rearrange that to get U initial plus K initial is equal to U final plus K final. So that's another way that you could use conservation of energy, and it's also closer to the method that I use. Okay, but I just wanted you to understand that that's where that came from. Now, you can also deal with conservation of energy, even in the case when you're dealing with some forces that are what we call dissipative forces, or non-conservative forces. So, if non-conservative forces are included, then you can address that by saying delta U plus delta K is equal to the work done by non-conservative forces. Okay, so that is another way you can go about doing this, and all of those three are really what the way that your book does it. Okay, they all work, and if you like them when you're looking at your book or your author's examples of problems and you understand that really well, if you want to use that, that's fine. I'm going to give you the way that I've been doing it since I was an undergraduate, because I just found that was the most convenient, and I didn't have to worry about nitpicky things like, whether the sign's going to be positive or negative. So in my version that I'm getting ready to write, what you remember is you're never going to have anything be a negative term unless the following conditions occur. So if you happen to be using this particular potential, then you can obviously see that there's going to be a negative included. In fact, the zero of potential energy when you're using this one has already been defined to be zero at R approaching infinity. So you don't even have the freedom of choosing where the potential energy is zero, like I had told you before. And in fact, it's very normal for you to get nothing but negative energies. Okay, so keep an eye on that. That's a reason for you to have a negative. Now, another reason to have a negative is if an object ends up going lower than where you called y equals zero, then yeah, it's going to come out to have a negative potential energy. So that can occur, but you're not ever going to put them in intentionally to get the negatives. Okay, you almost always are going to choose some lowest point in your whole motion as the y equals zero case, in which case all your potentials will be negative. But if you actively try to choose one and have an object that goes lower than your y equals zero case, then yeah, you're going to bring in some negatives. So now that you know that, to use mine, your terms are all positive except if you use that U, or if you do one of those goofy things where y equals zero is not low enough, then here is my way. I should probably write with a pen instead of a laser pointer. So I'm just reminding you that I just gave you in this video exactly what conditions would make one of your terms turn out to be negative. So I'm just saying except dot 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 because I just finished explaining it. But what I use is I say U initial plus K initial, excuse me, plus work that you put into the system is equal to U final plus K final plus here I include E loss. So basically, if you have any frictional forces or other types of dissipative forces, but generally just frictional forces, you can sum them all up, make sure they're positive, and put them right there in that E loss term, and that will take care of it. But I also add another term that is work out. So what I do is I introduce this and tell everybody about it being each term being positive, and then I usually show a very typical example and show us using it several ways so that you'll understand. The key point about this is you want to one take into account each type of energy that arises uh, and do so exactly once. In other words, you like if you find that there's friction, you want to make sure you put friction in there. But if you end up counting it twice, then you're going to mess up. So it's very and that sounds like something stupid that you think would never do. But the problem is when you have these terms like E loss, there might be three different things that I could list under E loss, and all three of those things could also be listed under workout. So some of us might put one under ELOS, two under workout, two under ELOS, one under workout, all under workout, or all under ELOS. And in doing that, you might accidentally count the same term twice. You want to make sure you avoid that. So you got to count every possible exchange of energy for from one type to another, but you have to account for it exactly one time because if you do it more than once, that'd be a problem. So it does take into account each type of energy that you're going to have, and two, you got to make sure uh, each term. I don't think I'll say it. Each term can stand for several different types of energy and different terms. In other words, I'm trying to say here that even though I have U initial, that U initial could be represented by 1 half kx squared and mgy. So having it be one term in my equation, in my version of the equation, doesn't mean that it's exactly one term. That one term could represent three different ones. That still didn't look out so good. So hopefully that gives you some sense of what I'm talking about. Now that I've have that written there, I'm going to go ahead and do my typical example, which often seems a little bit cruel, but basically I start off with a child being pushed on a sled at the top of a mountain, and we're going to assume that it's more or less frictionless the whole way down the mountain and up at the top of the mountain. But then at the bottom, there's a very specific area where it's a high friction count, and then it will have like some kind of spring loaded backboard or bumper or something that we could use to bring the child child to a quote unquote safe stop. But what normally happens, because I make these numbers up sort of intentionally large and goofy, mainly just to give you an idea of all the different terms that we could use and how we could use them. But the big thing is it comes out where you're getting a kid on a sled going high speeds in which they could really get hurt. And it's not about that at all. It's just about me coming up with different terms and trying to make something memorable. So I'm going to go ahead and start with the problem. And what I'll do is I'll start by drawing a picture. So what we're going to have is at the top of the hill, there's some fairly level ground, and then it slopes down, and I'm going to make it real sharp so I don't take up so much of the page. And then it comes off gradual like this, and all of that surface is fairly frictionless. But then all of a sudden we hit rough terrain, and then we're back on a smooth surface, at which point we run into some kind of bumper mechanism that is spring loaded. Okay, so I'm going to say the K for the spring is equal to 1.20 times 10 to the fourth newtons per meter. So that's my spring constant. I'm going to say the height from here to here is H is equal to, let's say, 200.0 meters. Notice I put that extra zero there so that everybody would understand. I definitely got three sig figs here. I try to use always a minimum of three sig figs. Uh, Over here, I'm going to say mu kinetic is actually equal to 1.11. So we're going to actually imagine that this is a really rough area that's almost like the emergency off ramps that you see for Mack trucks when you're driving through the mountains. They normally would have them where they pull off, and sometimes they go uphill, so that has a tendency to slow them down. But not only that, instead of them having pavement, they'll have it with just deep, deep sand. And in so doing, you can bring a runaway truck down to a stop pretty quickly. I am going to say that this distance right here, I'm going to call this distance D2, and I'm going to say it's 100.0. Actually, no, because I'm going to use something else. I don't want to. I'm going to say this is 95.0 meters, and that's to the end of that part. So what I'm saying is that little sandy area that we're going to use to try to slow down the child, that's only 95 meters long. And ideally, we would like to figure out, if it's going to come to a complete stop on that particular spot, or if it's going to make it all through it and then run into the bumper and stuff like that. So we've got this, and now in addition to these drawings, I've got to show you what's going on at the top. So I'm going to have a little sled. There's a little sled. There's going to be a child on it. Uh, you can think of it as a little Mr. Younger, even though I wasn't fat when I was a kid. I'm fat now, so we're gonna we're gonna say it's a fat kid named Mr. Younger. All right. Now the neat part is we're gonna have the kid's father giving him a push, and the father is going to push them a distance D1 equals, let's say, 2.00 meters, and the father is actually applying a force, let's say F sub D for dad, is equal to, let's say, 100.0 newtons. And we're going to say the boy plus the sled has a mass of 100.0 kilograms. Obviously, I've got some kind of fascination with multiples of 100. Okay, so that's what's going to happen. The child is sitting on a sled at the top of a mountain, and he's not moving. So initially, we have nothing but potential energy, and that would be in the form of m times g times y, where probably instinctively you'd think we should choose y to be 200 meters, and that would be a good choice. Now, if we started studying it at the instant that the father stopped pushing it, then the initial velocity would not be zero, even though the potential energy would still be zero, would still be the m times g times 200 meters. Okay, so we've changed that a little bit, but in addition to the father applying that force, and I'm showing it horizontally so that really with this work being done by the father, it's really just a F times delta D. You don't have to do the integral because the force isn't going to change. You don't have to do the dot product because the force is parallel to the displacement and all that good stuff. Now, what we want to know for part A is what is the velocity right there just before it goes into the pit of sand stuff to slow it down. We'd like to know what velocity is at the end. So this is question A, is what's the velocity right there? Then uh, our next question, part B, is uh, D2. Oh, darn it, I hate it when it happens. D2 equals question mark or velocity final 2 equals question mark. So what I mean there is when we push this child, he's going to go down the incline and speed up because he's going downhill, and he's going to reach some higher speed VF1 just before he goes into the rough patch. Now, that rough patch might be enough to bring him to a stop, in which case I want to know D2. But if D2 is not enough to bring him to a stop, then I want to know what its velocity would be when he leaves the rough patch. So I'm going to write this right here and say VF2 equals question mark, and I'm going to say D2 equals question mark, and put an R there, and I'll just put B here so we understand what I'm talking about. And then finally, we're going to, if it actually makes it fast enough to get off of the rough spot with some velocity, then we're going to wonder what D3 is. And actually, I think I'm going to make that in a different color. I'm going to choose black. And now we're going to say this is D3 equals question mark, and that's going to be part C. So we have a couple different scenarios. We know that the object is at a bare minimum going to make it into the rough patch. So we want to find out what the velocity is just before it runs into the rough patch. That's part A. No matter what, we're going to find out that. Part B, I either need to find out how far along the rough patch it'll make it before it comes to a stop, in which case I can just solve for D2, or how fast will it be going when it leaves the rough patch, because clearly the rough patch was not tough enough to slow it down to zero. And then finally, once it makes it through the rough patch, assuming it does, then we need to see how much the spring is going to be compressed by the child being brought to a stop. Now, we're imagining that basically this, as the kid hits the spring-loaded board or whatever, it's going to push it shut, or, well, I should say, compress it, compress it, compress it, compress it until it comes to a stop. At that point, we'd have some kind of mechanical mechanism that would actually stop the spring from pushing back, because obviously that could be just as traumatic for the child if they, hit it at 150 miles per hour and brought themselves to a stop. That's going to be a rough stop. But then imagine going from 0 to 150 miles per hour backwards immediately after that, and they shoot you back up the hill. So we're going to try to avoid that by imagining the spring is actually going to be compressed but come to a stop. So my solution for this is going to be me making use of my version of conservation of energy, which is U initial plus kinetic energy initial plus work in is equal to U final plus kinetic energy final plus E loss plus W out. So again, we all can use this and we all can disagree on what the different terms are. For instance, you might say that the friction due to that little sand pit is work out. I might call it E loss. As long as each of us account for it exactly once, we should still get the same answer. It doesn't matter. Okay. So that's what I mean here. So let's get started. And we're going to start off by calculating the work done by the father, which I'm going to call work in. So work in equals work done by dad. So the work in is going to equal. And remember, we're always going to keep these terms positive. So even if you calculated a negative work, you'd still say, okay, the way we've got it set up with Mr. Younger's equation, I'm going to take the positive. But in this case, the force I told you was 100.0 newtons. The distance is 2.00 meters. And the angle between them is 0, so we would write cosine 0 degrees, and this should give us the answer in joules is 200.0 joules. So that's the work done by father. We have that. We can calculate the initial potential energy as well. That's just equal to m times g times h. So in this case, it's going to be, remember, this is supposed to be the kid plus the sled plus, all his winter clothes and all that stuff. So that's why I made him 100 kilograms. Plus, he's supposed to be, a little fat Mr. Younger. So that works out pretty well, too. 100 times 9.80 meters per second every second, and then times h is 200.0 meters. That gives me whoa, Nelly, need a calculator for this. That gives me 100 times 9.8 times 200, or excuse me, 2.00, not 200. Ooh, that's what I did wrong. Hold on a second. Oh no, that was MGH, so that's cool. Yeah, I'm sorry, I forgot. I was thinking the 2 meters that we did for the boy being pushed, but this is literally a height of 200 meters. So this is going to give us like 98 grand or something like that. 1,000, no, 196,000. So I'm going to call this 1.96 times 10 to the fifth joules. So that's the initial potential energy. So now I can fill this out. What I'm going to do is say the initial kinetic energy for part A is 0 because I'm starting at looking at the boys starting from rest, dad giving them a push. If I wanted to figure out what the boys' velocity was at the end of the push, I could do that. But the only terms I would have there is just work in on the left side and K final on the right side. So I've put K initial equals 0 here because I'm thinking of it the instant the father starts to push them. I'm counting work in as what the father did. So that's why I went ahead and calculated that. I can now put in UI, we said was 1.96. Oh, I should be writing in black. Sorry about that. 1.96 times 10 to the fifth joules is U initial. And then the kinetic energy is 0, but the work put in by the father is 200.0 joules. So that corresponds to work in, that corresponds to U initial. Now, the U final, since I called U initial MGH, that means Y equals 0 corresponds to the height at the very bottom. So that's what I'm using for it. That means this kinetic or this potential energy is going to be 0 there. Now, at the bottom, we're just trying to figure out what the kinetic energy is. And notice for part A, we're not going into the frictionful part and we're not going into the spring compressing. So there will be no energy loss and there will be no work out because in my brain, I'm currently thinking E loss would have been the friction force, and I'm thinking W out would be me compressing the spring, or me as a child compressing the spring. So that's why that worked out that way. I'm going to go ahead and write this equal to, because we've already done the left hand side, it's going to be equal to 1 half times 100.0 kilograms times V final 1 squared. So that's the velocity that we'll have just before the sled enters the rough area. So with that, we can take our 196,000 and add 200 to it. That's more or less just outside of the sig figs, but we're going to take count of it and play a little fast and loose with the sig figs. So this gives me 196,200 joules, and then I'm going to divide both sides by, so 196,200 joules. I'm going to divide that by 50.00 kilograms. That's from the 1/2 times 100 that's happening here. In this case, I'm dividing by 50.00 kilograms as well. And then you can see that V final would equal the square root of this number. So we're going to say the square root of 196,200 divided by 50, and that gives me 3,924. And that gives you a joule is a Newton meter, and a Newton is a kilogram meter per second squared. So a joule is a kilogram meter squared per second squared. If I divide out the kilogram, I just get meters squared per second squared, which is exactly what we want because if you take the square root of meters squared per second squared, you get meters per second. And technically you get plus or minus, but we only care about the positive sign. So now I'm going to take the square root of that answer. As soon as I find my square root key, oh, there it is. Nope, that was not the right one. As soon as I find my square root key, oh, there it is. Shift square root, shift answer, and that gives me nothing useful. 62.64 meters per second. That is not a good number for the small child. And again, that's in meters per second, but that's the velocity. So we're going to say VF1 is equal to 62.641 meters per second. Technically speaking, I should have had really only 3 sig figs. So that would leave the 4 and the 1 as not sig figs, and this is our answer to part A. Now, remember that's about 2.237 times that is the velocity in miles per hour. So that's 140 miles per hour. This is not good. Poor little fella. Poor little Billy. He's definitely gonna lose his hair. Ah, too late. No, I'm just playing. All right. So let's go to part B now. Does everybody understand that part A though? Does that make some sense what we did? No questions? Okay, so now this is again what's kind of neat about this problem is now for part B, I'm trying to decide is the energy that is stolen from by friction by them running through the 95 meter wide rough section. If that is over this 196,200 joules, then it's not going to make it to the end of the rough section. So what I need to do is calculate what the total rough section E loss is. So I'm going to do that right quick. Let's say E loss with a H for hypothetical, meaning assuming we cover the whole space. Now, remember, the E loss is supposed to be the force times the distance again, using work equals the integral of E dot ds or E dot dl or whatever. In this case, everything's parallel. Technically speaking, the friction is anti-parallel, so it's 180 degrees, and therefore the E loss would normally come out to be a negative number. And again, in my paradigm where I'm using this little equation, we just treat it as positive. And the reason why is because I put it on the right side. If I wanted to account for it on the left side, I'd have to put the negative in. So that's all been thought out ahead of time, and you just know it'll work. So the E loss is going to be the friction force, which is mu kinetic times the normal force. And whenever you're on a level surface and no forces are pushing down or up on you other than just gravity pulling you down, the normal force is just the weight. So we're going to do that and we're going to multiply it by D2. So I'm going to say 1.11. That's a very high coefficient of friction, especially for kinetic friction. It's normally the static friction is a bigger one, but bigger than one is a big deal. Okay. The normal force is supposed to be mg, so that's going to be 100.0 kilograms times 9.80 meters per second every second. And so now I've got mu times m times g, and now I got to multiply that by 95.0 meters. And that gives us, of course, joules. So I'm going to take 1.11 times 100 times 9.8 times 95.0, and that's going to give me 103,341 joules. Now you can see that that is clearly less than what we had before, which was 196,200 joules. So it will definitely make it all the way across. So we don't have to calculate D2 as if it were a variable. We have to calculate VF2. So in calculating VF2, we can refer back to the very beginning. So we can take that 196,000 plus the 200 joules and make that the left-hand side because we're taking into account just the initial potential energy plus the work that the father put in. Or we could just take the kinetic energy that the kid had just before they got onto the rough surface and from that figure out what it is. It turns out they're going to be the same either way because clearly the kinetic energy that the person had at the that the kid with the sled had at the very bottom is, and by the way, the energy includes the energy resulting from the sled's mass too. So it's really, you got to think that the energies are a property of the system, not a particular object. So we're going to do that second scenario where I'm just going to say, look, I know the energy coming in was basically 196,200 joules. So I'm going to do that and say for part B, left hand side is equal to 196,200 joules. And I will underline all three of those to remind us that that's not really uh, the all sig figs, in other words, because there's some of these numbers that aren't sig figs at all, specifically the underlying ones. Now, the using that as the left hand side is fine. What I'm going to do now is say 196,200 joules. That's going to equal, we can treat it basically as just, whoa, Nelly. We can treat it basically as just one half 100.0 kilograms times. Somebody's just pulling up at my house and I don't know why, so sorry about that. Shawnee, somebody's here. Oh, it looks like they might just be someone delivering a package, but they got their kids with them and stuff. Okay, sorry, sorry about that, everybody. So we're going to say basically the left-hand side is just due to the kinetic energy that the sled system had just before it entered the rough spot. So that's going to be 1/2 times 100 times our speed that we got, which was 62.641 meters per second squared. That's the left-hand side, and therefore all this is that number. Now, what we're going to have is the right hand side, which is UF, putting my back macro back on, UF is equal to 0. So I'm going to say 0 for that. Plus, I have kinetic energy final. Yes, I'm definitely going to have that, and that'll be 1/2 times 100.0 kilograms times, in this case, it would be what we called VF2 squared. So that gives me the kinetic energy final. There is going to be a E loss, and we already calculated that. So I'm going to say plus 103,341 joules. Again, treating those as non-significant figures, and then plus 0 because there's no work out. So does everybody understand what part of my equation, this one right here, what part of that this is? That's the main thing, is so that you have some sense of how I'm just repeatedly using the same equation. Let me make sure my chat's open. Anybody have any questions about that before I carry on? All right. So that actually allows us to take the 196,200 and subtract from it the 103,341. So I'm going to say minus 103,341, like that. Maybe she's going to a different place. Okay. That leaves me 92,859. So now what I have is 90. Whoa, might want to write with a marker again. 92,859 joules. And that cut us down to 2 sig figs. That's entirely just on the left hand side. That's equal to 50.00 kilograms times V final sub 2 squared. So I can take V final sub 2 by basically dividing by 50. Of course, whatever you do to one side, you got to do to the other. So I'm going to divide both sides by 50 and then take the square root. So I took the 92,859. I'm going to divide it by 50. And that gives me 1,857. And then I got to take the square root of that, 1857.18. We actually only had 2 sig figs there, so the 5418 is not any good. And technically, this is the plus or minus. So now that I take the square root of that answer, that gives me 43.10 meters per second. So we're now looking like 90 miles per hour. So still pretty fast, but that gives us our second answer. And I'm going to write it over here. Velocity final sub 2 is equal to 43.10 meters per second. And I'm going to box that off as part B. Any questions on that one? Okay, now that we have that, we're going to go on to the last part, because basically what's going to happen now is we know the system, which includes the child and the sled, are going to be past the rough spot. They're going to be moving at 43.10 meters per second, and then they're going to run into a spring-loaded board, and all that kinetic energy is basically going to be converted to potential energy of the spring, or work done in compressing the spring. All I have to do is take the total amount of energy we had going into that, which would be the kinetic energy. I could just do 1/2 mv squared again, or I could take what the kinetic energy was equal to in the last step, which was 92,859 joules. I can just say that's the left-hand side of the conservation of energy equation. The right-hand side is going to be work out in the form of 1/2 kx squared, because U final is 0, K final is 0, and E loss is going to be 0 here because, again, I usually use my E loss for friction losses. So let's do that now. Part C, U initial plus K initial plus work in. We know all of that results in, looks like my pen's starting to not write. Yeah, my tip was coming unscrewed. That whole left-hand side is basically equivalent to 92,859 joules, like that. And then the other side is equal to U final plus K final plus E loss plus work out. Again, we're not doing anything with friction, so you could, use work out or E loss to calculate friction losses. It doesn't matter which one, you'll get the same answer either way. So we could do that, but the point is, once we got off the rough patch, there's no friction again, and I'm assuming there's no friction under the spring either. So as the spring gets compressed and moves out the way, the system will be able to run through the additionally non-frictionful surface. So what we have here is that the U final is at y equals 0. So that's U equals 0. The kinetic energy, once he's completely compressed the spring, will be 0. And the E loss, which I would normally count, like I said, as friction, that's going to be 0. But this right here, the workout, is going to be 1/2 K, and then I called it D3, so I'm going to say 1/2 K D3 squared instead of 1/2 KX squared. So I can go ahead and plug that in. It's going to be 0 plus 0 plus 0 plus 1/2 of the K I said was 1.20 times 10 to the fourth newtons per meter, and all that times D3 squared. So in this case, all I got to do is divide the 92,859 by the 1/2 of 1.20 times 10 to the fourth, and that's all we got to do. So 92,859, of course, then you got to take the square root. But anyways, 92,859 divided by, I'm not even going to take the time to, you know, figure out the 1/2 times 1.2. I'm just going to put it in my calculator. Left parenthesis 0.5 times 1.2 times 10 to the fourth, close parenthesis. And that gives me, again, before we take the square root, that gives me the distances, or the distance squared will be equal to 15.47. So I'm going to say D3 is equal to plus or minus the square root of 15.477 meters squared. And of course, when we take the square root of that, that becomes square root, oops, that becomes, ooh, that did not work. So 15.4765 raised to the 0.5 power gives me 3.934 meters. So that means the little Mr. Younger fat kid on the sled will compress the spring by about 3.93 meters. Okay. We did probably lose all but 2 sig figs in the process, so technically it should probably be about 3.9. And again, I'm trying to estimate that as best I can because most people don't care about the sig figs, and I'm certainly one that doesn't, but I'm trying to do it in case you have an instructor that is being careful about that. The biggest error comes in, like I said, when you start to add and subtract numbers and you're using sig fig rules, mainly because students forget that it's not the number of sig figs when you add or subtract numbers, it's the number of decimal places that matters. So, does anybody have any questions on this sort of comprehensive use of this version of the conservation of energy equation? All right, I want to check something real quick. I don't think I did this last time, or was it? Did I do it? Mm, yep, I didn't do it. Okay. That's cool. I was curious if I'd done something that I normally do. I think I'm going to do it now, though. So here's another example, and this one I'm going to do without numbers. I'm going to do it what we call, symbolically or theoretically. Uh, so I'll get a completely general answer for any values of M and G and all that good stuff. But what we're going to do is we're going to imagine that an object is falling with some initial speed. Okay, so let's say we've got a building, and this is an area where we can ignore air resistance, say, and let's say a person threw a ball straight downwards with a velocity initially as let's say 10.0 meters per second, and the height was. Now I put a number there, so we'll actually be able to calculate it later. But I'm just going to call it VI for right now, mainly because I forgot that I wasn't going to do numbers. But I'm going to put the numbers here. That'll give us a nice little backup to make it a realistic thing. Let's say the height is about 5 floors, so that would be roughly 50 meters. That's close enough. So I'm just going to call that H. Nope, I'm going to call that Y0. That's what I should call that. So let me do this. So I'm going to say this is y0 is equal to 50.0 meters, like that. And now I can shrink this back down and draw the rest of my little arrow like that. And what I want to figure out is just before the ball hits the ground, what is V final? Okay. No air resistance. And the question is, what is the final according to conservation of energy? Okay. And we can go ahead and say that the mass will be M is equal to 1.00 kilograms, even though, again, we won't necessarily need it. Uh, so I'm going to start off with my conservation of energy equation. So we'll write solution. My conservation of energy equation is UI plus KI plus work in is equal to U final plus K final plus E loss plus work out, like that. So there's my whole equation. I've got U, whoa, Nelly. I've got U is equal to mgy. I've got K is equal to 1/2 mv squared. In this case, work in equals E loss equals work out for me is all going to be zero because this is air resistanceless and I'm just using potential energy versus kinetic energy to account for everything. So now I'm going to go ahead and put my terms in. Again, starting with UI plus KI plus work in equals U final plus K final plus E loss plus work out. And that zero, the final potential energy would be mgy, so that'd be mg times zero equals zero, and work in would be zero. The initial kinetic energy is equal to 1/2 mvi squared, and the initial potential energy is mgy. So I can go ahead and fill all this stuff in. I'm going to say m times g times y0. That's the potential energy term. So just in case anybody doesn't understand, we do that. I'm going to say that's the potential energy term plus 1/2 mvi squared. So that is the kinetic energy term. Now this is going to be equal to m times g times zero. That's just me being pedantic, but pointing out to you that I am taking into account the final potential energy, but it's zero. Now I'm going to say plus 1/2 m v final squared, and that v final is what we want. So we're sort of acting like we know everything else. But the big thing to notice here is that I can divide both sides of the equation by m. The only rule against doing that, generally anything you do to one side of an equation, you can do to the other. So that includes, multiplication of one side by a number as long as you do it to the other side. In this case, division works as well, but you're not really technically allowed to multiply through by zero, for instance, or definitely not allowed either to divide by zero because you never can divide by zero. M has no chance of being zero, so we're not doing that. And there are some times where you can run into problems by accidentally multiplying by zero, but that's usually very rare, and you don't have to deal with it except on, like I said, really rare occasions that you're probably not going to do. But I'll tell you, if you ever see one of those neat little tricks that you'll see like in a newspaper or something where someone says, let's take your age, do this, do that. All right, is the number you now have your age with your height or year of birth after it or something? Whenever you have those little word games, a lot of times I've figured out that they are doing, sad things like accidentally. Well, in those cases, they're almost always just a simple formula. But in the cases where you end up getting a weird identity like 4 = 7, it's because you multiplied through by zero. Anyways, sorry for going so far afield. Let me go ahead and do this. Now that I've divided through by m, you can see that we get g times y0 plus 1/2 vi squared equals 1/2 v final squared. So now I'm going to multiply through both sides by 2. And in doing that, I'm going to also reverse it. So I'm going to say VF squared is equal to VI squared plus 2 times G times Y0. That's the main reason I did this symbolically, is I wanted you to see that that answer came out. Does anybody recognize that answer or that equation that we got? Okay. Well, it is, and probably y'all are listening or whatever and knew the answer, but just didn't think to reply. But basically, it's just one of the kinematic equations. The one that we got after we integrated twice, we ended up having x equals 1/2 at squared plus v0t plus x0. Well, if you had that equation and you used A is equal to VF minus V0 over T, if you solve the A equals VF minus V0 over T for T, and then plug that in the X equals 1 half AT squared dot 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 equation, you'll end up getting this equation after the work. So that's kind of a nice thing to see that when we're doing methods that had nothing to do with basically the calculus of kinematics, but had a lot to do with this new concept of energy, ended up giving us the exact same result we got from kinematics when we imagined throwing a ball downward with an initial velocity and wanted to see what the final velocity was. So this is the answer for part A. Now for part B, let's go ahead and calculate exactly what this final speed would be. So for part B, we have V initial was equal to 10.0 meters per second. We're going to have G, since I've sort of been treating down as positive, I'm going to go ahead and say down is positive and call this 9.80 meters per second every second. And then the Y0, of course, is going to be 500 or 50.0 meters. So I can get VF by taking the square root of VI squared plus 2G Y0. So that's going to be the square root of 10.0 meters per second squared plus 2 times 9.80 meters per second every second times 50.0 meters. So notice the meters times the meters per second gives you meters squared per second squared, just like the 10 squared did. So the units are definitely matching, and because we're adding, that's critical. So we got that. Now we just got to take it and see that the ultimate results will be meters squared per second squared under the square root. So that does give us the meters per second. And the answer is 10 squared plus 2 times 9.8 times 50. That gives us 1080. Now, if you were doing a projectile motion problem and you were solving for, a particular height, and then you'd actually have to use the plus or minus square root, and then you'd have to use some logic or reason to try to figure out which one of those it would be. In this case, we're just dropping it down, so there's no ambiguity whatsoever in whether it's up or down in terms of velocity. But we've got 1080 meters per second, and I'm going to raise that to the 0.5 power, and I get 32.86 meters per second is the final velocity, and that should be only good, I'm thinking, to 3 sig figs if the addition under the square root didn't mess up things too much. So, any questions on that one? All right. Well, another thing you have to be able to do, and we've got another 10 minutes. Another thing you got to be able to do is, as we showed in those five mathematical statements, the last one being there exists a scalar potential U such that F is equal to the negative gradient of U. That gives us a prescription for figuring out what the force is given a particular potential energy. So I've already showed this one at least once. I don't know if I showed it just in class or what, but I'm going to do it again now. But if you imagine the potential energy we were just working with, we had U of Y is equal to M times G times Y. We did know that that was a result of the gravitational force. So the name of the gravitational force that's acting on us is called our weight. So it's really the weight. So the formula is mg with that one. But what I just claimed was F is equal to the negative gradient of u. This gradient actually is a what we call an operator, or at least that's the way I like to think about it. There's other things you can think about it as well, but right now I like to think about it as an operator. And you'd say it's an operator that would be defined such that you're expecting to put something to the right of it. That's what I mean by an operator. It's like you have to leave a space or some kind of like normally if you just said f of parentheses with nothing inside the parentheses, that would be saying, "Hey, I'm treating this function like an operator because it has to have some kind of input, what you're going to put in between the parentheses to get an output." So that's what's going on here. What it would be, and this is kind of weird, but you'd have to write the I hat first and then you take the derivative of whatever's to the right with respect to x. So notice the space that's to the right of the triangle, the upside down triangle, is just like the space that's to the right of the backwards looking 6 in that derivative. Uh, Same thing happens in the y term, so I put the j hat there, but this time it's the partial with respect to y. And the same thing happens with the k hat term, and that's it's partial with respect to z. Again, you're expecting something to be to the right of it. In the case of this function y, u of y, it only has one variable, and the variable is y. So you really only need that one term, j hat partial with respect to y, even though I wrote it j hat partial with respect to x, because clearly I'm a goober. Nope, partial with respect to y. So now let's actually do that. So f is supposed to be equal to, I'm going to write it like this. F is equal to the negative gradient of u. So f sub y would be the negative partial of f with respect to y. Okay, that's sort of spelled out from just looking at the line above it, but I think it's pretty self-explanatory. Hopefully, it won't bother you by me jumping to that. So, fy is equal to the negative of the partial of the function, or excuse me, there I go with the function. It's not the function, it's the potential energy. I said it right to the left of there, but in other words, this part was right. I don't know why I put an F there. But anyways, now we're back to this. So this is going to be the partial of u with respect to y. The negative is going to come out in front, and now I'm going to say the derivative, because u only depends on y, the partial derivative becomes the same thing as the regular derivative. So it's a partial with respect to y of m times g times y. Now, I'm taking a few liberties here by assuming that since m and g are an object's mass and gravitational acceleration, they're fixed numbers. But in some sense, you could have pretended this potential energy was a function of m, g, and y, and that would lead to a bunch of problems. So just ignore that. You're really more thinking about it as the kinematic variables x, y, and z are the relevant ones. So, anyways, when we take the derivative of mgy with respect to y, we're going to get just mg. So that's going to give us the negative that was already there times mg. And if you look again at this formula, you see that this term is what we're dealing with. So I should just take that number and put it next to j hat, and that'll make the force. So finally, you see F is equal to negative mg and then j hat, which is exactly the weight. Because we learned that to calculate the weight, you have to take mass times gravitational acceleration, lowercase g, and then it's a force that points towards the center of the Earth, which in this case is going to be in the downward direction. So that's it. Hopefully that makes a little bit of sense to you. That's how you actually do it. Now let me show you with a little bit more robust problem. So the more robust problem is going to be uh, if u is equal to, let's say, a times z over, let's say, q squared plus z squared, where z's the only kinematic variable, so that's the only one we got to worry about anyways. Uh, what is f sub z? So that's a question we can ask. Okay. We know that according to that theorem that we were talking about at the beginning of class, we know that, and I'm going to do a different color now. We know that F is equal to the negative gradient of the potential energy. We've been given a potential energy function here, A times Z over Q squared plus Z squared. So if I want the Z component of it, I know the Z component is equal to the negative partial of U with respect to Z. So I'm going to calculate that now. F sub Z is equal to the negative of partial, in this case, with respect to Z, of the way I like to write it is I'm just going to put AZ times Q squared plus Z squared to the negative one, like that. And the reason why is by writing it this way, it's a multiplication, and I can completely avoid even trying to think about the quotient rule for taking the derivatives of a fraction or of a fraction basically. I was going to say a division problem, but that was being pedantic. So the A can come out in front for starters. So I'm just going to put the negative A out here. But in doing the product rule, I can take the derivative of the first one and just multiply that times the second factor plus the derivative of the second factor times just the plain first factor. I can do that now. So I'm going to take and break this out and write that the partial of z with respect to z is given by that, but that's where I'm taking the derivative of the first factor. Now that's going to be multiplied by what is left of the multiplication, which would be the z squared plus q squared to the negative 1 power. Now I'm got to take the derivative of the other factor. So this time I'm going to leave the z, but I'm going to take the derivative with respect to z of q squared plus z squared to the negative 1. And that's what I got to do. So we're finishing right about the time. We got about 2 minutes. You are free to go, of course, if you need to. So split, that's not a problem. But here's a negative a. This first term is just going to become 1 over q squared plus z squared. This other term over here is going to turn out to be z for starters. We're going to take the derivative of q squared plus z squared to the negative 1. That would be a negative 1 times. Now we got to take the q squared plus z squared and make that or raise that to the negative 2 power. So it's now going to become q squared plus z squared in the bottom, and it's squared because when you take the derivative, you have to subtract 1 from the exponent. So that gave us a negative 2. But I also had to multiply it by the negative 1 that was the exponent initially. So I get a negative 1 times z there. Now I also have to use the chain rule, so I got to take the derivative of q squared plus z squared with respect to z, and that is just 2z. So that's what my total factor is here. I can still leave this AZ out front, but I'm going to go ahead and pull it in instead. And what I get is A over Q squared plus Z squared. Now the next one is a minus because of that negative one that came in there. And now I'm going to get 2A z squared over q squared plus z squared, but this denominator will be actually squared. So we could actually get a common denominator by multiplying the top and bottom of the left fraction by q squared plus z squared. That's all I'm going to do with this. You guys are, of course, free to go. I will finish that out right there, but this problem is complete as it is. It's just some algebraic manipulation to make it look like the solution. Uh, more similar to the one in the book or more similar to one that you might see. So I'm going to continue doing that, but you guys are free to go. Daniel did have a question. If he's got lab or if anybody can stick around, we'll go ahead and solve that problem too. Otherwise, I'm just going to make a video about it and post it for you guys. So thanks for coming, everybody. And it was Daniel, wasn't it? Was that you, Daniel, that had to ask me the question from problem chapter 7? He might not be here.
Yeah,
Oh, it was you. Okay. Do you have time or you got lab now?
I have time.
You say you don't have lab? Oh, you have time. Gotcha. Sorry about that. I couldn't hear very well. All right. So let me just finish this up real quick, just finishing this last step, and then I'll go ahead and do the problem. So I'm going to multiply the top and bottom of that first fraction by q squared plus z squared. So that's going to become a q squared plus a z squared. And then the numerator over the other side is just minus 2a z squared like that. And then all of this will now be over q squared plus z squared. And all of that is raised to the 2 power. What we see here is I got a common factor of a, and then, ooh, it's supposed to be a z squared there. I don't. I kind of did something like a z squared. I did a to the z power. I don't know what happened there. Anyway, so 2a z squared. So this 2a z squared subtracted from a z squared gives you negative z squared. So I'm going to say this is just plain q, or excuse me, a times q squared minus z squared over q squared plus z squared to the 2 power. And that's it. Okay. All right. You didn't have any questions about this, did you, Daniel?
Mm,